Okay, so a few words about logarithms in the TFAE theorem. It's not actually called the TFAE theorem, that's just what I call it because I need to be able to refer to it. So logarithms. Logarithms should be, if you remember your calculus, inverses to exponentials. Okay, so what do we mean by that? Well, we know some mapping properties of exponentials. Properties. In particular, e to the z. Because this is one of the homework assignments. So what we know about e to the z is if you take a vertical line, and we'll call this x equals a, then e to the z maps that to a circle. And the radius of the circle is e to the a. If you take a horizontal line, y equals b, e to the z will map that to a ray without the origin, and the angle of this will be b. And that's because e to the z is e to the x plus iy, which is e to the x times cosine y plus I sine y. If you keep x constant, then you're going around in a circle because you're varying y. If you keep y constant, right, then you're fixing your angle and you're varying your distance from the origin. So e to the z is e to the real part of z times cosine imaginary part of z plus I sine imaginary part of z. So fixing the imaginary part means you're moving radially, fixing the real part means you're moving in a circle. Okay, so what that means then, if I take a horizontal line, say y equals b, then that horizontal line, like we said above, gets mapped to an angle b. So then if I take the horizontal line y equals b plus 2 pi, that gets mapped onto the same angle. So this interval of 2 pi on vertical interval on 2 pi gets mapped to the entire plane except the origin, because e to the z equals 0 has no solution. So that gives us a bit of a problem, which is if I pick any particular point in the range of e to the z, there'll be some point, a plus ib, that gets mapped to this point, and this point will have a r, which is e to the a, and angle b. But if I go vertically upwards to a plus ib plus 2 pi, I get another point that's mapped there. And if I go down a plus I, b minus 2 pi, I get another point that's mapped to this. Because every time I wrap around by 2 pi on the range, this is 4 pi, right? Every time I go around here by 2 pi, I pick up another point. And that corresponds to going up and down vertically in the domain. So all of these points get mapped to the same point. And the point is, e to the z has no inverse because it's not a one-to-one function. But it's not one-to-one in a very specific way. So one can actually sort of define an inverse we can define an inverse to f is equals e to the z on a particular strip. So if I take, there's B, and then we'll put a dotted line up here because we're not going to include this one. But that's, yeah, y equals B. And then this is y equals B plus 2 pi. Okay, so this strip, we know e to the z will map this part to array. And then we know this interval gets mapped to the same array, but we're not actually, that line gets mapped to the same array, but we're not actually going to put it in. But if I take any vertical line here, what do I get? I get a circle. And so if I look at all these vertical lines, that fills in the entire plane. And so now on this particular strip, e to the z is one-to-one, and so it has an inverse, right? And the inverse is the logarithm. So how do we go about defining the logarithm then? Well, if you remember defining inverses for sine and cosine, you know you have the same problem, right? You have infinitely many possibilities to choose from, and we make a choice somewhat arbitrarily. So the principal branch of the logarithm is denoted with a capital L log. And we say, okay, what we're going to do is we're going to go from y equals pi, y equals minus pi. This bottom line is supposed to be dotted because we're not going to include it in our domain. Our domain is just from pi to minus pi. And so e to the z will take us pi is here, and every vertical line takes us like that. Great, so now this is one-to-one. This is called a branch. This is called the branch cut. There are infinitely many branches, right? This is another branch, right? Every choice of strip that's 2 pi horizontally gives you a different branch. And it has a different branch cut, and the branch cut is the angle that you cut it at. So what does logarithm of z do? Logarithm of z is defined on the entire plane except the origin, and it maps the entire plane into this branch cut, into this branch. And this is the line y equals minus pi, it's the line y equals plus pi. Right? And so there's our branch cut. And the formal definition is we want log to behave the way it usually does. So right? And if you remember your logarithm rules, right? Log of a product is a sum. Log of e to the I theta is just whatever that is. Keep in mind that we restrict ourselves to r greater than 0. So ln, that symbol is the usual ln because on the positive real numbers. And you can write this in terms of z itself as log of z equals logarithm of the modulus of z plus I times capital A arg of z. And the problem with it is you can imagine if I go down a path, a circle like this, right? And so along this path, my argument is going to pi. And so that corresponds to a path going this way. If I go the other way, my argument is approaching minus pi. So along this path, we're going that way. And so what that means is that this particular point actually gets mapped up here, right? Because this bottom line is not part of the thing, part of the range. And if I take a small circle around that point in the domain, that circle gets cut in two, because the bottom half gets mapped down here, the top half gets mapped up here, and so we have the problem with logarithm, which shows up in a different number of different places. Log of z is not continuous on the branch cut. And so that's the basic mapping properties of log of z, and one of the problems with log of z. And we'll see that in a couple of different contexts that 0 is a problem. And associated with that problem is going around 0, and the discontinuity in log of z is part of that. So way down here somewhere, we have this theorem, the TFAE theorem. And these are two theorems that we talked about in class, but not, I hadn't put up in lecture notes on. So if D is a domain, f of z is continuous on D. And so keep in mind that a domain is open and connected. Then we have the following things. And f is a function that's continuous. So f of z has an antiderivative if and only if path integrals along f of z are path independent, and it can be evaluated just by integrating. And if gamma is a closed smooth path within D, then integral around gamma of f of z, dz equals 0. These are equivalent. If one of these things are true, all three of them are true. That's why I call it the TFAE theorem. The following are equivalent. They don't have to be, right? If one of them is false, then all of them are false. If one of them is true, then all of them are true. This is a very useful criterion. And note, I can connect these two if I know f of z has an antiderivative. I know two things. One is that integral around gamma of f equals 0 as long as gamma is a closed path, and integral along paths that aren't closed. It's pretty much like the fundamental theorem of calculus. Take the antiderivative, plug in the ending point, plug in the starting point, and subtract. So as an example, let gamma equal the unit circle. F of z equals z to the 4th sine 7z. What's the integral around gamma of f? Well, This has an antiderivative, and you know it has an antiderivative because you've taken calculus 2 and you can grind through that. It's an integration by parts 4 times, something like that. But this is a closed path. We know that it's got an antiderivative. If it's got an antiderivative, then the integral around a closed smooth path is 0. So that's 0. So it allows you to integrate things pretty quickly. On the other hand, if you know that the integral around closed smooth paths are 0, then you know it has an antiderivative. And I don't think we did that part of it that much in class. The Cauchy-Grassat theorem is also a very useful theorem, and especially in context of this, is if we have a function that's analytic in and inside a path gamma, then we know the integral is 0. So So suppose f of z is 1 over z, right? And we know that this has a problem. It's not analytic at z equals 0, right? But this circle, right? A circle with center 10, radius 1, gamma does not go around 0. So what's the integral around this circle of 1 over z dz? That equals 0 because the place where we're not analytic is not in the center, and so 1 over z is analytic on and inside that, and so the integral is 0. So the Cauchy-Grassat theorem then tells us if you're analytic, right, if you have a domain where f of z is analytic on and inside every single closed loop gamma, then the integral is 0. But if the integral is 0, right, if that's true, then you verified part 3 of the TFAE theorem. It tells us that we have antiderivatives. So analytic functions have antiderivatives on places where they are analytic. Note that this condition log of z violates that, right? So if you take D to be the entire plane without the origin, log of z is not continuous on that. You have to cut away the branch cut to be able to define an antiderivative of logarithm of z. So that's the following is our equivalent theorem and the Cauchy-Grassat theorem, which we had worked on in class a little bit. It was stuff that we did after spring break, actually. And so, I mean, the lectures were after spring break, but we did do them in class a little bit. And so I think that's all that you would need for the test. Let's see now.